today's my presentation will be on basics of quantum gates, and I'll also take you through the applications of quantum computing and what are all the gates that is available. Why do we have the quantum computing to be a threat for the present day security issues and things like that. So this is Anitha, professor and head of the Department of Computer Science and Engineering, Sri Venkateswara College of Engineering, Sri Perumbudur. So let me get into the introduction to quantum computing. So the quantum computing basically uses the quantum mechanics to solve all the problems, and there are a lot of quantum mechanics available. And this is not going to be a new topic. In fact, it is residing right from 1920s. So people have started working on that, and Einstein has been one who have started working on the photons and the neutrons, electrons available. And basically, the quantum computing is all about the electron movements, how the electron spins and what is the rotation and how it rotates, what are the spheres that we consider, all those stuff works on that. But one history is like the Einstein does not believe on the the movement of the electrons with a very good speed and the entanglement that is available. And it's the Bell who has come up in the future and 1980s and 85s. He is the one who has provided the information that there is a entanglement that is available. And I'll tell you what the entanglement is all about, and how the people work on the entanglement, and is it really an entanglement available, and how quantum works on the entanglement. Okay, and I'll also take you through the application and some of the a practical experience of how the gates has been generated, and how the block spheres work, and how it is going to get the different types of qubits that's available. Okay, so basics of quantum mechanics. So definitely it is the superposition that allows the qubits to be in multiple states at the same time. For example, I could say that when a coin is tossed, you have a head, you have a tail, but at the same time the probability of the head and the probability of the tail. But the superposition is one that where the coil be available in both head as well as at the tail. So we'll go through some of the diagrammatic representation of the superposition, and then we'll come to know about it. So the basic is superposition and entanglement. So entanglement is basically, it creates a correlation between the classical limits. To say when something happening here, it has an impact on the other way. For example, I could say that there is a meeting that's happening today. When my internet goes off, what will happen? Will there be any kind of changes that will happen in the other end? I'm a presenter and you're all listening, you're a participator. Okay, so when there is a problem in my internet, will there be any changes at your end? Will you witness anything?
The presentation will stop.
Yeah, the presentation will stop, and now we could not able to continue, right? So which means that one impact the other is what we call it as an entanglement. So some event, we celebrate Diwali, we celebrate Pongal, we celebrate all the festivals here. So it's not only happening in India. A Tamil people who is who is residing in the other country is also celebrating, which means it has an impact. The day has an impact. The day Pongal has an impact, where the Tamil people residing in Chennai, the Tamil people residing in any part of India, any part of the country, any part of the other other country is also celebrating, which means that one event have an impact on the other is what we call it as an entanglement. Then we will talk about the interference. What goes wrong? What comes right? Because when you say you are creating so many bits out of this quantum computing, and we have an opportunity to share so many bits to the users. So what is right, what is wrong will be taken care by the quantum. Okay, so these are the basic mechanisms that is involved into quantum computing. So superposition, entanglement, and the interference. My dear friends, if you have any doubts, please stop me here. I'm not going to take no the hard and fast rule of quantum computing. It's going to be the basics. Okay. So basically, what is quantum computing? We know what is quantum mechanics. What are the basics that is residing in the quantum mechanics, and we'll come to know about what is quantum computing. It's the information theory plus the quantum mechanics makes the world to enter into quantum computing. So information theory is the computer science and the communication, and no the physics. We doesn't know the physics that is behind it, but basically it is purely physics that is going to bring it into matter. And the classical mechanics is the base. So what I say, the superposition, the entanglement, and the interference is going to bring in a lot of impact in the quantum computing. And the basic terminologies. So we should know about quantum bits, we should know about the quantum state, we should know about the quantum superposition, and we should know about the quantum entanglement. So these are the basic or the technical jargons which makes the quantum computing to bring up, and the technologies associated with the quantum computing and the concepts that is associated with the quantum computing. So we will get to know about what is a state and what is a superposition. So there are two things. One is the classical computing, what we have now, and another one is the quantum computing. Just a minute. Yeah. So this is basically about the state and the superposition. So we have the classical computing and we have the quantum computing. So can take this. The classical computing, you could see here, this is the coin that has been tossed. Okay, so we have the head or we have the tail. So we have two bits here. One is 0 and another one is the 1. So either we get a head or either we get a tail. And another example is it's a smiley, which has a smile and which has a sorrow. So when you are smiling, it means that there is no sorrow. It's like an atomic operation. When one is available, another one is not available. It's a mutual exclusion. When I take this as a transistor, when there is a switch, if the switch is on, which means that it is not off. When it is off, it means that it is not on. So this is what the classical computing that is existing. But now, what is the quantum computing? What are the basic states of the quantum computing? We say two things. One is the 0, another one is the 1. Okay, so you could see the representations here. The 0 is represented as one line, 0, and the angle symbol. We could also say it's a greater than symbol. Okay, this is how the quantum computing is going to be represented henceforth, because whatever we see the gates, whatever we see the superpositions, it's going to be determined like this. So this is 0 state and this is 1 state. Okay, and these are the basic states. It's not superposition. These are the basic states that is available with the quantum computing. And this is a smiley, this is with sorrow, and this is a thing that's open. Okay, when an electron wants to flow, it's open. The bulb is open here and it's closed. Okay, which means that it is not open, right? These are the quantum computing states. Now we'll see about the quantum superposition. When you toss a coin, okay, when it landed the earth, you could able to say that it's a head or a tail. When it is in your hand, you could say it's a head or a tail. But when it is in the tossed position, it's tossing. Okay, you could not say it is a head or it's a tail. So there is a probability of alpha can be a 0 and beta can be a 1. So there is a possibility that it can be an alpha 0 or the beta 1. So now the superposition has been written like that. So psi is a state. Okay, psi, quantum state is represented like this. Psi is equal to alpha of 0, we doesn't know. Alpha may be no any constant value, and beta may be any constant value, but it is going to be alpha plus beta, and which put together is going to be 1. Okay, the probability may be 1. So alpha 0 plus beta 1. So this is going to be the state and the superposition. Okay. So now we'll take the n qubits. Okay, so this is going to be the superposition. So when I take psi, what will be the no expression to relate to the psi? A naught, because this 0 represents there are a lot of bits available. So we can take the 1 bit, we can take 2 bit, we can take 3 bit, 4 bit, and so on. Okay, so A naught. We say alpha plus beta, but it may be of any expressions. A naught can be a 0, or a1 can be 001, and so on to a power 2 power n minus 1. Okay, so these many states are available. So in nutshell, we could say a naught of 0 of 10 plus a1 of 1 of 10 plus a2 power n minus 1, 2 power minus 1 of 10. This is for a 10 state. Okay, so basically your superposition is going to be represented for n qubits like this. Okay. Now, we should know about the quantum entanglement. So, as I said, it started in the year 1920. It's not new. The quantum theory or the quantum mechanics started in the year 1920s, and 1935. Einstein has its own paradox. He says that no, there is no kind of entanglement available. Okay, when you take a green color water bottle, it's going to be green always. Okay, it's not going to change its color. But when you take a red color water bottle, it's going to be remain the same, and there is no changes is going to happen. So that is going to be the theory of the Einstein. Okay, so but later Schrodinger works on the entanglement. So he says, I think all these are the physics that you might be read from your no 12th standard and in your higher educations. But let me say what is Schrodinger effect says that when a snake and a cat are put into a basket, there is a possibility that the cat may exist or the cat may die. Okay, so he calls this as an entanglement. There is an interference. No, one impact the other. When the snake bites the cat may not no live. When the snake does not bite the cat, there is a possibility that the cat may live. So the effect of the snake may remain on the cat. So this is what we call it as an entanglement. So later, Bohr's principle also worked on that, and it is the Bell's inequality which makes that yeah, there is an entanglement that is available. And he has given a theory that whenever the entanglement is greater than 2, okay, which means that there is an entanglement available. So there is a Bell's inequality equation available, but let's not go in depth into what the Bell's inequality says. But there is an inequality equation which says that whenever the value is greater than 2, because the 2 is a value. You should understand why I'm telling this 2, because 2 is going to be taken as a value in the quantum computing. So from where the 2 comes, many of the readers may not understand from where the 2 comes, but basically it is by the Bell's inequality. So whenever it crosses 2, it may be 2 root 2. Whenever it crosses root 2, 0.707, which means that there is an entanglement. So the first level of entanglement experiment happened in the year 1980. See, the quantum mechanics started in the year 1920, but the entanglement experiment has been done only in the 1980s. I'll also let you know where are the experiments happening and how many qubits are presently available, what will happen in the 2033 in my future slides. Okay. So this is what we call it as a normal computing. You could see here, these are the decimals. So probably you might be knowing this. So 0 is represented 000, 1 is represented 001, 2 is represented 0010. So it is based on the bits 0, 1. Now, whatever computing we have now, that the Intel processor is working currently is now basically on 0, 1. So the objects are represented in binary code, or it is processed in the binary code, and these binary code represents are represented by bits zeros and ones. Okay, so basically you might be knowing about this, and this is how the memory is going to handle all this computing. Okay, so whenever we want to work on the value, let me take 1. Okay, so which means that 001, so 1 is logged here. When I take the value 2, 0010. 10 is logged in the memory. Okay, probably it may be 0010, or sometimes it's 10, because the 00 may not be taken as an effect here. Okay, and to say 7, it's 0111. This is how it has been interpreted in the normal computing. But is it going to help you in the quantum computing? Definitely it is not, because we does not know what the state is. Here we know 0 and 1, so I represented it as 0 and 1. But when it comes to quantum computing, there may be a lot of bits that may be happening, because when I say head or tail, it may be 0 or it may be 1. But when I go for the quantum computing, it may be 00000 or 11111 or 010101, a kind of representations, right? See, this is what we call, this is a normal bit. Okay, this is going to be a normal bit or regular bit what we use now. And this is going to be a quantum bit. You could see here, 0 takes 1. Sorry, 0 takes a red color and the blue takes the 1. Okay, now when you take it as a qubit, this is normal bit. Okay, 0 and 1. But when you take a qubit, so this is, you could see here different colors, blue and the red combines together. So which means that psi is equal to, the alpha may be 0, the beta may be 1. So this is what we call it as a qubit. And this sphere is what we call it as a Bloch sphere. So BLOCH, Bloch sphere. And this has its own representations. It can take any angle, it can take any sign, it can take any cos, because everything is going to be measured with a frequency. Okay, frequency basically it is a sine wave. Okay, so we may take any kind of wave. One wave follows the other is going to happen in the quantum computing. Whereas in the bit, it is going to be discrete. We don't have any waves here. But whereas here we go with the waves. Just understand this. It's a Bloch sphere. We'll see how this can be practically experienced. Okay. Now, this is the another structure of the qubit. So it can be 0, it can be 1. Okay, so you could see here the qubit can be of anything. Okay, it can be 0, it can be 1. Why it is mentioned as a sphere is, it can take any of the directions. Okay, so 360 degree of rotations it can have. It can have any kind of angles. It can be a quadratic, it can be pi by 2, it can be pi by 4, it can be pi by 8, anything it can take. So that's why it is called as a qubit. Okay, so now you should understand the importance of the qubit. So a qubit is a quantum bit that can be in a superposition of 0. You could see I didn't write 0 alone. It is the quantum state. The quantum state is represented with the line 0 and the greater than symbol and 1. So it is represented as psi, alpha of 0 but beta of 1. But whereas the alpha square plus beta square is equal to 1, because the maximum probability that it can extend is 1, right? So it can be visualized on a Bloch sphere. So this is what we call it as a Bloch sphere, where it can take any of the angle. Okay, just remember, this is a Bloch sphere. Okay, so this is a geometrical representation of the pure state space of the two-level quantum mechanical. So it's a two-level because I take only alpha, I take only beta. Okay, and it is named as Bloch after the physicist Felix Bloch. Okay, so now you know about the bits and you know about the qubits, right? Now we'll see about the another important jargon, that is the quantum tunneling. So what makes the quantum tunneling now? Only because of the quantum tunneling, the processor is going to take up multiple work. Actually, so when we talk about the quantum computing, we talk about the quantum cryptography, we talk about all those stuff. But basically what it is a transistor. It is going to be a semiconductor, right? So initially, this is how the entanglement happens. When the size is higher, the barrier, the interference is higher, the electron, we consider this as an electron, and this electron cannot move from A to B. This cannot move from A to B because it has a big barrier, right? Then when later dates goes on, the barrier gets smaller. So 0 will remain here. But now the barrier is very smaller. So what happens? The electrons started moving continuously. So when the electron starts moving continuously, that is where this entanglement position will come, because you could see this. So this will start moving. It's not going to be in one place. It's going to be moving like this from here, 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 here to this place. Okay, so this is what we call it as a barrier. So almost it is going to be 500 nanometer nowadays. Okay, so that is where the quantum computing comes into picture. Okay, so quantum computing is not the field only for the computer science. It's going to be the field for the electronics, the electrical people. Everybody is going to work on the quantum, because basically it's the quantum tunneling that makes the electron free movements, and we work on that. Okay, so quantum tunneling is a phenomenon that underlies the operation of silicon spin qubits. So the spin is an important terminology where the electron spins. The electron spins may from up and down, and the electron spin may from down to up, and right to left and left to right. The spin may happen. So India's Intel strategies used to use its manufacturing and architectural strength to develop a practical full stack quantum system. Is it available now? Yeah, it is available, but not to the fully expected value, right? Then I think you might be knowing about what a superposition, what a quantum state is all about. And now let's see about the quantum gates, because the gate is very important, and these are the gates that is going to work on the quantum states. So let me take the basic quantum gates are Hadamard gates and CNOT gates. There are a lot of gates that I'll let you know one by one, but the basic gates are the Hadamard and the CNOT. So all the gates, quantum gates, work basically on the principle of the C naught. So the circuit sequence of gates manipulating the qubits, and quantum gates manipulate qubits. These are the gates which is going to develop the qubits. So you might be probably knowing about the OR gate, AND gate, XOR gate, NOT gate, NAND gate. Likewise, we are going to have C naught, which is going to be a controlled NOT gate. Okay, so circuits are the sequence of gates performing the computations. So this is going to be the logic gate. So this is going to be the logic gate. Okay, so we have two inputs here. One is the control input, another one is the target input. Okay, and which is going to have a C0 representation, and it is going to give a target output. So control input, target input will provide you the target output. Okay, so let me take the symbol. C0 is a logic circuit quantum gate symbol. Control is represented by dot, and the target is represented by an XR symbol. You might be knowing this one, XR symbol. Control plus the target. Okay, this is going to be the basic C0 logic circuit. Okay, I think the time permits, I could show you the no the code of how to generate this logic circuit. Okay, so this is going to be the C0 logic. Okay, so controlled not. So basically all the quantum gates work on this controlled NOT gate. Okay, so the controlled NOT gate is represented as Q1. Q1 will be Q1. That's the output. That is the controlled input. This is going to be the target input. So controlled input will remain as a control input. We are not going to do any changes here. Whereas in the target inputs will be XORed. So whenever the target input is 1, it will give 0. Whenever the target input is 1, there will be a change in the output. Okay, so let me see here. Take an example. We are going to take A, B. Q is equal to A, R, B. Okay, so you could see here it is 0, it is 0, it is 1, and it's 1. And B is 0, 1, 0, 1. This you know, we are going to have a 2-bit. Okay, so when I take this, so when the controlled input is 0, no changes will happen in the target input. So it's going to be 0. Okay, because this is the controlled, this is going to be the target. When the controlled is 0, there won't be any changes in the target. Now this is 0, this is 1, there's no changes. But when you take this controlled input as 1, what happens is your target is 0. Now your target flips. Your target 0 will be flipped into 1. Hope you are able to understand. Yeah. I request an acknowledgement from the participants.
Yes, ma'am.
Yeah, thank you, sir.
Yes, ma'am.
Yes. So this is another controlled input. When the control input is one, your target input is flips. So one will become zero. So this is how the C naught gate is going to work. So this is the basic principle beyond the C naught, and let us see what are the gates that is available by making use of the C naught gate. Okay. So you could see here 2-qubit gate, control plus target. This is control, this is target. Whenever the control is 1, I have a control. The control is 1, my target flips. I have a control 1, my target flips here, right? Now, we'll see the matrix representation of the qubits, how the matrix representation is going to happen. So, in the qubits, 0 is always represented as 1 and 0. Okay, so 1 is always represented as 0 and 1. So, this is going to be the matrix representation of the qubits. Please assume 0 is 1, 0 and 1 is 0 and 1. So, now psi is equal to a of 0 plus b of 1. Remember alpha plus beta. Okay. So a of 1, 0 is my state plus b of 1. B of 1, right? So we'll take 0, 1, 1. So b of 0, 1, 1. So it just do the matrix multiplication. A into 1, A into 0. A 0 plus b into 0, 0, b into 1, b. So when you do the matrix addition here, so we will get A and B, right? This is what the matrix representation of the qubits, right? Now, this is another representation. Okay, so whenever we take C naught control for qubit 2, okay, 0, we will take. So qubit is 0, bit is 0 or 1. But qubit may take any value. It may take 0, 0, it may take 0, 0, 0, it may take 0, 0, 1. But in the quantum, everything works at a time. Okay, it's not one after the other, it works on the time. Okay, so when I take 0, 0, it is 0, and your A is also 0, your B is also 0. Okay, so now when you work on this, okay, so when you work on this, how do you represent 0, 0? How do you represent 0, 0? 0, 0, 0 is represented as 1, 0. And this 0 is also represented as 1, 0. So when you do the matrix multiplication of these two, we will be ending up with 1, 0, 0, 0. Okay, now we'll take 0 and 1. 0 is represented as 0 and 1. 1 is represented as, sorry, 0 is represented as 1 and 0. 1 is represented as 0 and 1. When you do the matrix multiplication, it will be ending up with 0, 1, 0, 0. I'll show you in the next diagram. Okay, so this is going to be the diagram. Okay, so your C naught control qubit circuit for 2-bit is 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 0, 1, and 0, 0, 1, 0. Okay, so this is going to be the qubit. Okay, so could you able to understand this, how this is working?
Yes, ma'am.
Yeah. Now, so I have given an explanation. See, when you take 0, it's 1, 0. When you take 1, it's 0 and 1. Okay. So I said 0, comma 0. So what is the value for 0, comma 0? It's 1. It's 1, 0, 0, 0. How does it come? So I take 1 into 1 by 0 into 1 of 0, because 0 is represented as 1 or 0. Okay, 1, 0 into 1, 0. Just do 1 into 1, 1 into 0. 0 into 1, 1 into 1 is equal to 1. 1 into 0 is equal to 0. 0 into 1 is equal to 0. And 0 into 0 is equal to 0. So this is what the matrix has been calculated. So finally, it will end up with 1, 0, 0, 0, 0, 1, 0, 1, 0, 0, 0, 1, and 0, 0, 1, 0. I think if time permits, you can work on that. Okay, 0, 0, 0, 1, 1, 0, 1, 1. Right? So this is the matrix representation, how your C naught control qubit work for 2-bit. Okay, so basically the quantum logic gates, There are a lot of logic gates that's available. Okay, the important logic gates are poly X gate and Hadamard gate. So basically, many of the people will work on the Hadamard gate. Okay, so this is the representation of the poly X gate. Poly X gate, X is equal to 0, 1, 1, 0. So we said 0 separately, 1 separately, but the poly X gate will take 0, 1 and 1, 0. And Hadamard gate will take X is equal to 1 by root 2. Okay, 1 by 0.707, because you remember the Bell's inequality. What I said is, if it is more than 2, then there is an entanglement. So that is what the next value is taken as 0.707. That is root 2. Okay, 1, 1, 1 minus 1. So this is the representation of the Hadamard gate. Okay, so basically what is Hadamard gate? It's a single qubit gate. It transforms the computation basis into 0 and 1 into the equal superpositions. Okay, so the matrix representation is represented as 1 by root 2 into 1, 1, 1 minus 1. Okay, so this is a poly gate, and this is going to be the Hadamard gate. Okay, now we'll take x of 0, 0, 1, 1, 0. 0 is represented as 1, 0. So multiply this by 1 and 0, then we will end up with 0 and 1, which is a 1. And x of 1, 0, 1, 1, 0. 1 is represented as 0 and 1. You just do this, you will end up with 1 and 0. 1 and 0 is basically 0. Okay, so x of psi, this is going to be the superposition. So x of superposition will be 0, 1, 1, 0, and I'm going to take a and b. In spite of 1, 0, 0, 1, I'm going to take both the condition, because I say in the superposition, it may be a or it may be a b. Okay, I take a and b, which will end up with b and a. So this is called as an poly X gate. Okay, so basically you should remember 0 is represented as 1 and 0, and 1 is represented as 0 and 1. And this is going to be the Hadamard gate. So this is the basic representation. Hadamard gate is equal to 1 by root 2 into 1, 1, 1 minus 1. And 1, 0 is equal to 1 by root 2, 1 by root 2. And h of 1 is equal to, it may end up with 1 by root 2 minus 1 by root 2. Okay, so this is going to have a negative impact, right? So this is going to be the Hadamard gate. Okay, so action on states, you get on 0, it's 1, 0. H of 0 is equal to 1 by root 2, 0 plus 1. And this means if you measure, you will get 0 or you may get 1 with an equal probability of 50-50%. But on 1, when you use this, h of 1 is equal to 1 by root 2, it is 0 minus 1, which is relatively a negative phase. So negative is also a superposition, because we express everything in the block sphere where you have a positive and we also have a negative phase. Okay, so this is going to be the action on the states. And there is another gate called as a Toffoli gate. Please remind me of the time. Okay, I think I'll go till 7:15. Okay, because we have started only by 6:15 today. Toffoli gate. Okay, so we have seen poly gate, we have seen Hadamard gate, and now we'll go ahead with the Toffoli gate. Okay, so Toffoli gate, again it works on the controlled C naught. Okay, so Toffoli gate expression is given as Q1, Q2, Q3, which gives Q1, Q2, Q3, and XOR with Q1 and Q2. So Q1 is a controlled, Q2 is a controlled. Okay, now I'm going to take Q3. It's going to be a target bit. The target bit will take the XOR of Q1 and Q2. So Q3 XOR of Q1 and Q2 will be your target qubit. So this is the basic representation of the Toffoli gate. Okay, so this is the controlled NOT gate, which produces the value for the C naught. You could see here 0, 0 and 0. So which is not going to take any flip. Whenever there is a flip in the target bit, then when we will have a flip in the when there is a one in the control bit, then only we'll have a flip in the target bit. Okay, so now we have the flip that's 1 and 1 in the target bit, and this 0 will be taken as 1 here. I think you can able to understand. Basically, everything is a NOT gate, but how the people work on different gate, using this C naught logic. Okay. Now, this is also a control input. This is also a control input. Whenever the control input is 1, the target flips. So now the target 1 will be flipped to 0. Okay. So this is another Toffoli gate. There are a lot of gates that's available. So you could take 000 gives 000 This is 001. Okay. 101, 1011, and this is 11, and the value will be flipped to 0. Okay. Now, so I think you are able to understand what the gates, what is the C naught logic, and what are all the gates available, because this is going to be taken as an obfuscation matrix in your quantum cryptography. Basically, all these no matrix kind of obfuscations and the mathematical representations is going to bring in a lot of changes in your quantum cryptography. Okay, so block sphere view will have a north pole, it may have a south pole. Okay, this corresponds to creating equal probability amplitude. Okay, you can see here the block sphere representation of the Pauli X gate. Okay, so 0 X. Okay, X of 0, this is the circuit representation. Okay, 0 1 1 0. So 0 1 1 0 and 1 0, because I have taken 0, so it's 1 0 is equal to 0 1, it's equal to 1. So this comes here, right? When it flips to the polygate representation of X of 1, it moves to the another line. So it is just opposite of this direction. You could see here, this is 1 0 and 1, this is in the another opposite. So which means that it corresponds to creating equal probability amplitudes. Okay, this is the block sphere of the Hadamard gate. Okay, so you could see here, I have Hadamard gate here. The Hadamard gate will be represented as 0, or it can be represented as 1. So positive, it goes in the positive side. When it comes in the negative, it comes in the negative. You remember, 0 creates positive and 1 creates negative. 1 by root 2, 1 by root 2, 1 by root 2 minus 1 by root 2. So this is negative. So this takes exactly the opposite direction. Okay. You may ask, ma'am, idella enna appdin kekkalam. These are all the sine and cos values. Okay. So it's not only the qubits, you can also go for the waves that may be represented in the block sphere. Okay. Hope I have done with the qubit. Now we'll enter into the quantum entanglement. So where is this entanglement comes here? So it's a direct observation while it builds inequality limits. The inequality limit is it should be greater than 2. When it violates 2, then I could say that it is into the entanglement position. Okay. So Einstein says that it's an assumed hidden variable. I could give you with an example. Okay, Einstein, what he proposes, there is a hidden variable. There are 3 assumptions, okay, corresponding to the mathematical. See, as of now, quantum computing and the entanglement has been proven only through the mathematical model. There is no practical model, but no, IBM has started working on that. Okay, so realism is a fixed property, whether seen or not. Locality, no faraway influence. Upper limit, there is an upper limit for correlation. Freedom of choice, measurement freely by the physicist. Okay, so when a classical world obeys all these, then we call it as an entanglement. Okay, so they are the father of quantum mechanics and the quantum which is existing nowadays, Charles Bennett and Gilles Brazard. Okay, so they have given some properties, and this is the man who is going to be called as the father of the quantum, where he is the one developed the quantum cryptography. It is first demonstrated in 1989 and discovered quantum teleportation, which means that a bit moves from south pole to north pole or north pole to south pole, is what I call it as a teleportation. So it is done in the year 1993. So please don't say that quantum is new. Quantum is not at all new. It's existing. Only thing is we are coming into the picture now because of the the limit in the processor that we use. Okay. So Bell's inequality says that. So whenever you toss something in a table, he says that the toss has its own gravity. Hidden variable is available. See, when you want to flip one, I think no, many of you have played what is this in Tamil? தாயம் ஓகே தாயம் விளையாடுறது. ஸோ வென் யூ ஃபிளிப் ஓகே எனக்கு வந்து தாயம் வேணும்னா நான் ஒரு மாதிரி தாயம் ஒன்று தாயம் ரெண்டு people used to say like that. And no, when you want to flip, sometimes we put very harsh, sometimes we make it very slow, which means that the pressure available in the hand, your mind is a hidden variable, your spinning is a hidden variable, your pressure that is given to the hand is a hidden variable. But whereas in the quantum entanglement, there is no hidden variables that's available. It's purely a random. Okay, there is no hidden variable, there is no external influence, only it is going to be proven in the mathematical way, right? So this is how a quantum entanglement resides. As I said, it's going to be in the waveform. Okay, so when I say psi of a, psi of b, one is not following the other. Okay, even with a very limited value. Okay, the red crosses, the blue starts and it's followed by the red. So there is a point where red and the blue will meet, and that position is what we call it as an entanglement position. So the red will have an impact on the blue will have an impact on the red. We did not know whether it's going to be a red or whether it's going to be a blue, or on what frequency it's going to be red and blue. But it's an entanglement that's happening here, and this can be proven only through the mathematical ways. Okay, now why the classical computer struggles? Because the classical computers will do only the sequential processing, that's one after the other, one after the other, one after the other. But whereas the quantum computers can explore many states at the same time. You remember the previous speaker in the day before yesterday, he said like, no, what is the superposition? A exists, A happen, B happen at the same time. A and B may also happen at the same time. So multiple states may happen at the same time is what we call it as a quantum computers. So polynomial versus exponential time, quantum algorithm like Shor's factor numbers exponentially faster than the classical algorithms. Okay, so the future of quantum computer, the quantum computer, the first was developed in the year 2023 with a 1,000 qubit threshold, boasting a total of 1121 qubits. Remember what we have seen in the previous slides is only 1 bit or 2 bit. Now it's going to be 112-bit qubits, and IBM plans to develop a 1 lakh qubit quantum centric supercomputer by 2033. But you should ask me why it's IBM. There are multiple giants. Google is also working on that. But no, why it's IBM? Because of this man who worked in the IBM fellow. He is the one behind the quantum, and that's why IBM has started its initiation in the quantum computing. Okay, so it's going to have cube 1 lakh qubit quantum centric supercomputer by 2033. Okay, so superconducting qubits, IBM is working, Google is working. The pros and cons are integration, the fast gate. You worked on the C gates, the C naught. You have taken so many gates. So which gate will work fast? Okay, and the cons is decoherence, because it's not going to happen one after the other. It's going to happen at the same time. So what will be the decoherence? And cryogenic cooling. See, when this, you remember, we bring in a server in the department. We need to fix an AC. That's the only for this processor. We have to fix AC and other things. You remember? Just imagine that much superpower is going to come up with one processor, and the cooling is going to really a challenging factor here, because it's integrated with circuits, fast gates, but requires cryogenic temperatures and are prone to decoherence. There are a lot of algorithms available. I'm not going to get into all the algorithms, but Shah's is one algorithm, Grover's is another algorithm, and Grover is going to be used for linear search. No, you go into the rack, you take the books one by one. But quantum, what it will do, it will send all the bits at the same time, and it will say whether it is available or not. Okay, so and variational quantum eigensolver. It's a hybrid algorithm where it goes to work on molecules. Okay, so we have come across now with a lot of chemical equations. We does not know which one works. So even the COVID, okay, it was not tested with the human properly because there's no time. The vaccines that has been developed at the time of COVID period, it's not no properly tested with human. And all this can become a minute work, a second's work, because of this quantum computing. A chemical reaction, the chemical changes in the molecule that's happening will be immediately witnessed through this quantum solvers, right? And quantum approximate optimizer algorithms is also working. Okay, and there are a lot of quantum machine learning that's going to happen. Quantum neural networks, kernel based methods, and ML algorithms. Okay, that's all going to happen. So these are the applications in the optimization, AI cryptography, supply chain, AI acceleration, breaking the entire classical cryptography algorithms that is existing. You say RSA, you say AES, you say any algorithm. No, this will definitely be taken care by the cryptography, and we have to provide such kind of cryptography algorithms. Because when people say RSA takes 250 days to broken, your quantum algorithm will take only a minute to break all the entire random numbers, because it's all built with the random numbers. And it can able to produce n number of random numbers at the same time. See, at Google, a quantum computer which is developed by the group Google can able to produce 53 qubits random numbers can be generated. Okay, so it says that the supercomputer will be doing it in 2.5 days, whereas the quantum computer will be doing it in 200 seconds. Okay, I'm saying 53 qubits, right? Just remember 53 qubits. How many bits have been generated? How many zeros and ones at the same time? Okay, so that will be broken within 200 seconds. So this is a proven statistic that's available. Okay, and all your QKD, that's BB84, probably secure communications, all these protocols are existing, and the current platforms to work with is IBM Qiskit, Google Circuit, and Rigetti Forest. Okay, so these are the platforms that's available, and these are the research challenges in quantum. It's not the quantum computing. Even with the quantum processor, we have a lot of challenges. Scalability is one of the challenge, noise and decoherence, algorithm, and the hardware match. How are you going to match the algorithms in the existing order? Because when I say hardware, enormous power has been available in the quantum processor. Okay, how do the algorithm matches? Okay, so these are going to be the real challenges residing with the quantum, right? So it's not the algorithm, it's not the quantum machine learning, it's not the quantum cryptography, it's not going to be the quantum. They're all one of the challenges residing for the algorithms or for the logics that's available. But the real challenge lies with the quantum processes. How does it go for the scalability? How does it work on the noise, decoherence, and algorithms? Okay, so these are the future directions and conclusions. Fault tolerant quantum computing is definitely a research challenge. Quantum cloud services, quantum AI integration, quantum computing is poised to revolutionize the computation, but requires continued research in hardware algorithms and the error correction. Okay, so these are going to be the future directions and conclusions. And these are some of the reference books available. Whenever you want to study on the quantum computing, just understand the logics and refer to these books. This is a book by the Riffel, Quantum Computing, a General Introduction, and Introduction to Quantum Computing by Wong. Okay, and whenever you want to learn the quantum computing, you should also refer to quantum mechanics. I think this book plays a vital role in understanding the quantum mechanics. Okay, so let me rush up with the a simple programs that get executed. Please tell me whether my screen is available. Is my collab is available?
Yes, ma'am. Yes, ma'am.
Yes, ma'am.
Yeah,
Yes, ma'am.
yeah.
Ma'am, yes, ma'am.
Yes.
Yes, ma'am.
So I told you about how to work on this. Let me show you how the sphere has been created. Okay. You remember the block sphere that's been created. Okay. Let me execute this. See, Quizquit is available. You can download it or you can work on the Google Colab. Only thing is, I have also encountered a lot of problems, and now I have fixed all the problems. I made at least no some 7 to 8 problems to work out here, but unfortunately, I don't think that the time will permit me. But anyways, I'll show you. Okay, so this quantum circuit, you have to import this, and we need to have a plot block multivector from Quizkit. You have to input the state vector and apply the Hadamard gate. I'm going to apply the Hadamard gate on qubit 0. Okay, so we will see the block sphere that's been developed here. You could see, where is that? See, this is how I encountered a lot of errors, and no, I fixed it, but let me see whether I could able to fix now. Okay, there's an error here. Let me see how I can able to fix this. Whatever no package that you need, you can pip install. Okay, that's a matter of time. Every package has been installed here, successfully installing, and yeah, I got this. Could you see this? This is a sphere. You remember I have told you the state vector. Okay, this is a block sphere with a qubit 0 with a qubit 1. Okay, now I've got this x-axis. Okay, so a lot of spheres. When I work it for one, I think it may go to the next direction. Let me check with that. Or no, you can try this if you want. I can able to provide this for you. Okay. Okay. Let me try this. I've not tried this. I work on qubit 1, 0, but not with 1. We'll see. No, there's an error. Okay, you can try this. Okay. It works for 0. Okay. See, don't say think that it's going to be only few lines, because you have every work is done in the Quiskit. Okay, the collab what you work is going to make use of the all the properties, all the functionalities that is available with the Quiskit. We just download the package and we work on that. Okay. Now I'll show you one more thing. That's the gate that is produced. You could see here, அங்க gate பார்த்தோம் இல்லையா? So 0 and 1. So this is going to be the controlled input. This is going to be the target input. So control input, what is the output? Target input, what is the output? Okay. So now this gets I've no executed this code and generated this. It's a generation of the no the gate that has been produced, and how many times this count says that the algorithm works for 492 times for 00 and 508 times for 11 to produce this gate. Okay, but this produces within a minute. See, you can see how many shots it gets executed. Thousand has been broken into these many times. Okay, 508 and the 492 something. Okay, this works. You take the header mat. Okay, apply the controlled gate bit. Okay, and this works on this. So for this, you need to import all the Quiskit, simulator, transpile, state vector, and your regular matplotlib. That and all, matplotlib, and a quantum circuit has to be downloaded, and the histogram is to give the count for you. Okay, and we will see another one. I'm sorry. I think I'm rushing because I don't find time. Okay, this is another circuit, okay, which has been developed, okay, using the block vector. Okay, so you could see here, this is the qubit 0. So I've generated H, X. Okay, this is going to be the 0 and 1. This is going to be the control input. This is going to be the target input. And this is going to be the state vector. 0.707. You remember this has been taken from the Bell's inequality. Okay, 1 by root 2. Okay, 0.707 plus 0, 0, 0, and 0. This is another value. Okay. So this is how the quantum gate has to be developed. Okay, this is another value that's been developed here with the floating point numbers with a dimension of 2 cross 2 comma 2. Okay, you can execute this and see what is happening. This is another gate that has been executed. Okay, so this is again q0, and here it works for 518 times, and here 11 executes for 506 times. Okay, so this is the NOT gate again. This is for the transpile that works here. Okay, there are a lot of gates available. Only thing is you have to take the NOT gate, apply the control gate and the target gate. 0 comma 1, 0 comma 1, 0 comma 1. Okay, and you have to work on that, right? Okay, this is another gate where 1 1 works for 497 times and 0 0 works for 5. See, every time when you execute, it may give a different, the code may be the same, but it may give a different count with the zeros and ones. It's basically on the block sphere, because there is an entanglement here, because one affects the other. Okay, right? Before that, you have to install the Qiskit and no AER. Okay, these are the packages you have to work on the Qiskit. Okay, I think I'll stop here and let me summarize. We have seen about what is a quantum mechanics, what is a gate, what is a qubit, what is a superposition, what's an entanglement, and what are the various gates that is available. So basically, it's the C naught that we work in, and what are the future directions which is going to be work on the quantum computing. Okay, so that's all my presentation. I think I have done a justification for 1 hour. Any queries?
Dear participants, if you have any queries, you can ask.
Yeah, yes, ma'am. Thank you for the wonderful session, ma'am. You have given a good insight about quantum computing.
Yes, ma'am.
I have a question. What is the real time, ma'am? Real time application, whether it has been applied in Chennai, ma'am, like in government sectors or non-government, in for a public usage, like
No, no.
social.
Now only the government has started its initiation, National Quantum Mission. I think if you are a faculty in an engineering college, the mission circular has been sent to everyone, and it requires a huge process, ma'am, which is with which costs a lot. Okay, so people have started working. Only it is in the simulator stages. Okay, so people have started working on that. I think government has given 30,000 crores of amount, 32,000 crores of amount has been allocated to this quantum mission. Okay, when
Okay, ma'am.
I think no, but the quantum computer, there's one more myth also, whether the quantum computer will replace all the existing processes. Actually, it is not. See, we do not need, see, to execute a data structure algorithm, we don't need a quantum processor. So there are some specific applications pertaining to quantum, and those applications is going to be executed using the quantum processor.
Okay, ma'am. The architecture is so very huge, like
Yeah.
it does of a room size, like.
Yes, ma'am. Yes, ma'am. See, actually, there is no proven method for the entanglement. Okay, it's all work on the entanglement, but slowly people started working on that. Okay, see, I know this quantum computing 2009 the IBM as the test bed அப்படின்றது வந்து people have started. I think 2009 for 10 20 years ஆப்போதான். almost or 15 years ಆಯ್ತು, right? So it's going on. I think very soon we will be getting it. So the quantum processors, and but definitely it will be used in the medical field. Okay.
Okay, ma'am. Even when it is in of room size, might be it's costlier, bit costlier, expensive.
Yeah, it's bit costlier, and the heat that is generated by the quantum processor will be really very high. So you have to provide the proper cooling facility. Okay, those things are there. Really, there are challenges with reference to quantum process. I think a lot of semiconductor industries have started working on that. Okay. So it may slowly progress. See, early days, the computer needs a glass room. It was a giant computer which is kept, and we know all those stories. Right now, it's no a hand device for everyone. Okay, so whoever has a mobile phone, they're all carrying a mini computer. So I think like that, there will be a progress definitely, but it may cost no time.
Okay, ma'am. That's what I have seen in a picture, in a Google picture. It is of many wires connected to it, and
Yeah.
is of a very huge size.
Many. You could see it's like that bottleneck diagram இருக்கும்ல, sandbox diagram. Okay, it will be like that because like so many cooling systems will be there. நிறைய qubits at a time. The bits will be moving like anything. Random number நீங்க வந்து ஒரு 200 secondsல generate பண்ண முடியும் அப்படின்னா it is really it needs lot of power actually.
Okay, ma'am. Thank you, ma'am. I think it's even very, very faster than the normal computers. Like, no, ma'am. It's
Yeah,
very
definitely,
faster.
ma'am. Definitely. So it's not going to work one by one. It's going to be work at the same time. Okay. Oh, one goes, the other goes. Not like that. Every time, every bit goes at the same time. Okay.
Okay, ma'am. Thank you so much, ma'am.
Thank
Thank
you,
you.
Preeti, ma'am. Thank you. Any other questions?
Ma'am, if no other questions, shall we wind up, ma'am?
Yeah, Isha, madam. Yeah.
Yeah, ma'am. Yeah. So, good evening, everyone. It is both an honor and a privilege to deliver the vote of thanks for today's insightful session on quantum gates and quantum insights. On the behalf of all the attendees, I would like to express my heartfelt gratitude to our respected HOD ma'am, Dr. R. Anitha, for taking the time to enlighten us with such a complex yet fascinating topic. Ma'am, your ability to simplify the abstract world of quantum computing, especially the working of quantum gates and their importance in shaping the future of computation, was truly commendable. Your deep insights and real world connection not only broadened our understanding but also sparked curiosity in many of us to explore the emerging field further. Once again, thank you, ma'am, for your valuable time, knowledge, and encouragement. Thank you so much, ma'am.
Thank you. Thank you, coordinators, and thank you, all the participants.
Thank you,
Thank
ma'am.
you
Thank
all.
you so much.
Thank you. Thanks a
Thank
lot.
you.
Thank you, ma'am.
Yeah, thank you.